So guys, let's do another topic from alcohol, phenol and ether, and this is about making you understand the difference between the structure of alcohol, phenol and ether. So what I will do, I will draw all these three structure and explain you all the perspectives related to each of them. So the first one is going to be alcohol, then it's going to be phenol and ether. So for alcohol, the simplest alcohol you can remember is the methanol. So a methanol has a structure something like something like this, where this oxygen is having the hydrogen and it has two lone pair right here, and this bond angle is 108.9. Now you do remember that this bond angle is slightly less than tetrahedral angle, which is 109.8. Okay, now this something also, this bond length is 142 picometer. This is 142 picometer. And then let's talk about the phenol. So a phenol has a structure like this one, a benzene ring, right? A benzene ring, and this benzene is having oxygen, as in a structure like this. There are two lone pair again, and this bond angle is going to be like 109, which is again less than tetrahedral angle, and this bond length between carbon and oxygen is 136 picometer. It's 136 picometer. Now draw the ether one and then try to get it. The simplest ether you can again remember is methoxymethane. So I'm drawing this methoxymethane. This is your methyl group, then you have oxygen, and then you have another carbon as a methyl group. So what is here? The bond angle in case of ether is slightly more than the tetrahedral, which is 111.7 degree, and this bond length is 141 picometer. 141 picometer. So we need to compare these three structure, and we need to find out why these structures are the way they are right now. So as you can see the structure here, and then you definitely realize that the hybridization of this oxygen is sp3. So it's sp3. Why? Because there are two bond pair with two lone pair, and this carbon is having a hybridization of sp3 again, right? So for carbon and for oxygen, the hybridization is sp3 and sp3. Let's talk here. The carbon is having a double bond, so hybridization for carbon is going to be sp2, but for oxygen there are two bond pair and two lone pair, so this time it's going to be sp3. So this describes the hybridization. Let's talk about the ether. Right, the carbon, each of these carbon is having four bonds around them, so it's going to be sp3, and the oxygen is again having two bond pair and of course two lone pair, so it's also going to be sp3. Right, now what you see that the alcohol and ether, they both are having hybridization similar. Why then the structure and then the bond lengths are different? That is what very important I need to talk to you about. Okay, let's start here. What you see, that the oxygen is bonded to alkyl group or a methyl group only from one side, right? So because that alkyl group is bonded here and alkyl group is having sp3 hybridization, this bond length is slightly going to be longer when you compare this particular one, where the bond length is only 141 picometer. So what conclusion is here? Because in the alcohol and in the ether, the oxygen is bonded to alkyl group, and that's the reason the bond length between carbon and oxygen is almost similar. This 142 and 141 doesn't seem to be widely separated. So that's why these two are having similar bond length, but this one is slightly less. It's because the oxygen is surrounded by two alkyl group here, right? Now let's talk about the phenol here, why the phenol is having a bond length which is quite less than the ether and the alcohol. It's because this carbon is having a hybridization of sp2, and what that means, that this bond between carbon and oxygen is having a partial double bond, right? So I'm going to write here, there is a partial double bond character between carbon and oxygen bond. So because this bond is having a partial double bond character, And what that mean, the electronegativity of this carbon is going to be much more. Similarly, oxygen itself is very electronegative. So because both of these atoms are electronegative, they are pulling the shared pair of electron with greater efficiency, and that's why the bond become very, very small, right? So the bond is becoming smaller here just because the hybridization of carbon here is sp2, and the bond is having a partial double bond character, and the bond length is going to be slightly less here. Now, after we are done with the bond length here, let's talk about the bond angle. What you see out here, that this bond is slightly less than tetrahedral, although if the hybridization is sp3, the bond angle should be tetrahedral, but it's slightly less than that. It's the only reason is that these two unshared electron here, these two unshared electron on oxygen, they are providing a kind of repulsive interaction, and that repulsive interaction is not enough to separate the two bond sphere around the oxygen to stay away. That's why it's slightly less than the tetrahedral. Now talk here, because this has higher electronegativity and there is no alkyl or aryl group here. So because oxygen can easily influence the shared pair of electron right here, and that's why the bond angle is going to be again slightly similar to that of phenol, to that of alcohol here, and going to be like 109. Now, but there is a problem. There are two lone pair here, two unshared electron. So the bond angle should be expected similar to those two, but why it's greater? Because there are two alkyl groups, and those two alkyl groups provide enormous repulsive force from coming closer. Remember, two similar groups apply a repulsive force that do not let them to come together, and if they are not coming together, the bond angle is going to be slightly greater than what is expected. So remember again that two alkyl groups, they have their own repulsive interaction. So what is happening? The unshared electron is not here providing a huge role, and that's why the bond angle is slightly greater than the expected value nearby 109 or 109.8. So this angle is slightly greater than tetrahedral angle. These two are slightly less than the tetrahedral angle. They have similar bond angle, but they have different bond length. Why they have similar bond angle? Because they have only one alkyl group to their one side. There you have aryl group, there you have the alkyl group. So that is what very, very important you have here, that why the bond length is different in these three cases, and why the bond angles are also different, right? So this was actually the motive of today's video. This is going to be very short, but I wanted to make you go exactly why the structure is that way before you even start learning the bond length and bond angle, right? So I hope you're going to study them, and you're going to get everything that is as per your requirements are. So thanks for watching, take care, and I hope to see you very soon in the very next video.